we'll talk about. Okay, see, we will continue our discussion on ship motion in regular wave. We will come to that a little later. First, let us now try to derive a formula for frequency of encounter. See, we know from regular wave C was given by omega by k given by lambda by t. Okay. Now, let us take a case. Ship is moving like this. Okay. And the waves are moving in this direction. See, this is my v. Let us say this is my wave speed. I think I should have taken another color. See, this, I don't know that this diagram might have become a little small. Let me try to explain. There is a ship here. What happened is that this ship is moving in this direction, speed v. Waves are coming in this direction with angle c, and we are going to call actually the vectorially the angle between this v vector and this vector to be equal to mu, the heading angle actually. You see, so this is my one vector one. See. This is my v vector and this is my c vector. Okay. So, v to c we are going to call, that is from this other axis, to be mu angle. Okay. Now, what is happening is that the wavelength of the ships are this. See, this is a crest line, this is a crest line, this is a crest line. So, the ship is the waves are moving along this direction with c, and this distance is a distance of crest line, and the period that the wave takes to move from here to here is c. Now, what is happening is that as the ship moves here, see, it meets a crest here and meets the next crest here, and this distance is lambda by cos mu. Okay. Now, Te, what we call encounter period, is going to be lambda divided, actually you can say other way around, that encounter period is how the ship is encountering the two crests traveling is two direction. Now, what is happening here, now if you sit on the ship here, the relative speed of the wave is going to be c minus v cos mu. See, c minus v cos mu in this direction. So, the encounter period is obviously the length lambda divided by c minus v, not cos mu. Mu is actually written here in this way. So, it is going to be here c plus, I will just write the way it is written here, mu minus pi. Okay. Because the way here that they have defined the mu here, it becomes this minus this v cos mu. Okay. Basically, we can work it out. Mu is actually written as this angle here. So, naturally mu minus pi becomes this angle. This becomes a mu minus pi angle, and so the relative speed obviously sitting from one to other is c minus v cos mu. So, it is c plus v cos mu minus pi, etc. Now, this is my Te. So, therefore, now again if I write Te becomes lambda by c minus v cos mu. This is a very elementary one, so I do not want to go too much on that. So, omega is becomes 2 pi by Te. This will become, if you work it out, it is 2 pi c minus v cos mu by lambda. This will become equal to k. 2 pi by lambda is k here. So, c minus v cos mu. Okay. Now, So omega E becomes here K into C minus V cos mu, but Kc equal to omega, because you see by definition C equal to omega by K. If you use that relation, if you use this relation, it turns out to be equal to omega minus K V cos mu. Okay. In fact, now if K equal to omega square by G, if you use this formula, because K is omega square, this is a famous relation that comes omega into minus omega square by V, oh sorry, not V, G V cos mu, or you can write is omega 1 minus omega V by G cos mu. This is the classical relation that tells us between the this thing, the between the relation between encounter frequency and wave frequency. If wave frequency is omega, you see this is the interesting relation I will discuss at little length. See, omega is the encounter frequency, omega E is, and omega is equal to wave frequency. So you will now cos mu equal to the heading angle, that is the vector angle between the two. Now what happened here? Let us go back to this relation here. Now mu, if this is the V and this is C, then mu equal to 180 degree. We call it head waves. When it is coming exactly like that, you see, when supposing, now here, I will just talk about this wave condition a little bit here, that is very important. If ship speed is here and the waves are coming exactly opposite, okay, then the angle between the two vectors is 180 degree, that is called head waves. If it came this way, that is C, then this is 90 degree, called beam waves, this or this, okay. And if it came this side C, then you call 0 degree following wave. Or more people will do it like this. The ship is moving this side. If the waves are coming this way, then mu equal to 0, 180. If waves are coming this side, mu equal to 90. Waves are coming this side, mu equal to 0. Waves can come from this side or this side or this side or this side. Normally what happens, if the waves are coming within this angle, okay, within this part, between mu is 90 to 180 or 270, you know, actually one sector is good enough, you don't go to, because of symmetry you don't go. If it is within this means the minus 90, you know, you can have the other side, we don't go for that. If it comes from this side, we call this to be head wave condition, because waves are actually coming in a direction. If you take any component which is actually the ship is heading into the waves, maybe less, but it is heading. This is actually exactly head wave condition. You can call this to be, people, the various terms, bow quartering C, this is beam waves, this entire thing can be called head wave condition. Exactly opposite is this thing. Why I am saying that is because in this angle the cos mu will become, see what is cos 180 degrees, minus 1. So cos mu here becomes a negative quantity. So in the following, in the head wave condition, cos mu is negative quantity. Okay, so that omega is become omega into 1 plus omega v by g into something. So that omega is become more than omega. This is what I want to tell here. On the other hand, if it is following wave condition, cos mu is a plus quantity, and you can see from here that this becomes a negative quantity, less. In fact, if I do a graph between omega e and omega, it looks something like this. See, if I say here omega and omega e, in head wave condition it goes like that. In beam wave, this is actually mu equal to 90 degree. This is mu, this side is mu more than 90 degree. It becomes something like that, you know, like for any omega there is a more, this is 45 degree line. So you get my point. In 90 degree there is a 1-to-1 correspondence. So if there is an encounter frequency is, you know, omega, absolute frequency omega, encounter is omega, same. That is because ship is going this side and waves are coming this side, so it is same, since relatively you are just going across the crest. But if you go actually into the wave, then you end up getting higher and higher frequency. That makes sense. Higher frequency means lower period. That makes sense. See, if you are heading into that, what was 10-second wave will appear as 8 seconds, 7 seconds, 6 seconds, depends on the speed. Okay, faster you go, smaller the period is. But the interesting part comes in the following wave, where the graph becomes something like that, which is very interesting. You will find this formula that in fact it can even become negative sometime, which we are not going to discuss. See, if you solve this problem with this is a quadratic equation, because it is bringing back that again, omega minus omega square by g v cos mu. This is a so-called quadratic equation. We need not go to this mathematics, but it turns out that in the following wave condition, there can be an omega which can be even negative. Negative omega means very interesting, because what happens, you are going in a ship here, waves are following, but wave speed is smaller than you. So if you stand here, to you it will appear as if wave is actually going on the other direction. See, you are going at say 10 meter per second. This is going as 8 meter per second. So if you stand here, you will think as if the wave is going away from you on the other side at 2 meter per second. This is what is meant by negative frequency. The physical concept of negative frequency. What happens is something like this. Suppose waves are coming this side. So obviously you are heading into it, so you are meeting the crest much faster and faster. As the waves come this side, you meet the crest at the same time. As it this side, you meet the crest lesser and lesser. As it is exactly same time, as it is exactly when omega 0, you meet like t becomes 0, you don't meet the wave, because you are going along with the crest. And if you are going faster, you actually have a hypothetical situation, because crest will appear to be moving away from it. Normally what happens, this is just to tell you general part, normally what happens, we are not concerned much about in sea keeping about the wave coming from following. We are mostly bothered about the head wave condition. Mostly because it is the head wave condition that gives large motions. Beam wave would give you large roll motion as you expect, head waves will give you large heave and pitch motion. And as far as societies go, largest bending moment etc. would occur more in head waves. And another thing we will see that as you are meeting the crest faster and faster, see, instead of 10 seconds you meet at every 6 seconds, your oscillation period is faster, so you are actually having a higher acceleration. It's more uncomfortable in many ways. So we will talk about that more. So this is what is encounter frequency. This encounter frequency is absolutely same as what is known as Doppler shift. In school physics, we have learned that when a train comes to a station, you hear that the whistle sound pitch goes up, because the frequency goes up. As it goes away, it goes down. In fact, this is very so common that you have even the theory called Redshift of Stars. Like the spectrum that we have electromagnetic, we have got violet to red, various frequency. Red is having a low frequency. Now, if the stars are moving away from you, then the light that comes would be shifting to a low frequency by this theory, and it will be the spectrum, the light will look more reddish. This is the fact that the lights come from the star looks reddish has been used to tell that the universe is expanding. Exact same Doppler shift idea. I am fond of telling relation with same thing with other areas, but same thing. It's the same encounter frequency idea which tells us why one of the theory why universe is expanding. Redshift of stars. Light that comes from that looks more red. That means that the star and earth distance is increasing. Therefore, it must be expanding. Okay, so this is a very common thing. Let us now look into now. Now we know. What we know now is that if there is a wave here, say I am calling eta as a cos omega t minus say kx or whatever. This omega t is the absolute wave, but if you sit on the ship, it will appear as omega t minus maybe kx. Okay, so therefore the excitation that will be obtained by the ship is going to be of this frequency, omega e frequency. So I can now write all the motion, say surge and all that, sway etc. I will just write one of them as if it will become n amplitude into plus a phase angle. See, I'll explain that to you. Say y is maybe sway, can be written as y, amplitude, cos, like that. I'll just write some of them more. Then roll maybe I can call phi equal to phi a. See, now this is all equation you find, all actually same equation. What we are saying here is like this. Now I want to find out if there is a wave here, how much the ship has a surge and sway and roll and heave and pitch and yaw. That is my aim of finding out ship motion in regular wave. Now I know that because my wave is the one that is giving my pressure, the pressure is all now being given at the frequency omega e. Therefore, my response also, when you add up everything changing at every omega e times or t e times, then the response and everything else also will have same kind of period. You see, you think of this. I have a ship here. Every point I have got a pressure coming. These pressures are changing, repeating exactly at te period, means encounter period. Suppose 8 seconds is my encounter period. Then every 8 seconds there is a pressure repetition. So naturally the force also will repeat at every 8 seconds. Therefore, the amount that is moves up and down also will repeat at every 8 seconds. Therefore, I can write the heave motion as if it is having amplitude Za and a cos function with period omega, frequency omega et. Of course, I don't know how much it is a phase. I have to add always a phase, because when you add them all up, you don't know the phase where it is. I will talk about the phase in a minute. What is the meaning of the phase, that I will talk about a minute. But this is the general form that I can write in a regular wave. When I have a sine wave which is regular, I must have all the motions which are also regular. So I know that with time they will, every 10 seconds or 8 seconds they will change. They will go like a 10 second. What I don't know is what is the amplitude, and what I don't know is what is the phase. I will tell you what is phase in the next diagram. That is when it is occurring with respect to wave. See, so this is a general form. That means I can represent actually when the waves are sinusoidal, everything else, everything of the shape response becomes also sinusoidal, because the simple fact, you break it down, all the fluid in the smallest particle, they are giving velocity, pressure, everything repeating at 10 seconds, that period. So naturally the result will also repeat at 10 seconds. If you have say 10 people are giving a push, and every 10 seconds you give a push, he gives a push 10 seconds. You sum them up, the net force is also every 10 seconds. This is what I want to tell. This is a very important physical concept that we must have in mind, that necessarily the response or force or pressure must be at the period of encounter at which the ship is meeting the waves. It is repeating. So you see the phase. Now this I need to draw slowly, maybe two graph. So I have got, let us say here, wave. This is, let us say, xi equal to, I am writing now xi a. This is the wave, xi a equal to xi cos omega t plus kx, let us say x equal to 0, some point I am taking, so it is like this. Now roll signal, let me take another color, roll signal. Roll signal is going to be, now here you see this diagram, this is my amplitude. See this, remember this is my xi a, okay, and this period, see here, if you take the time here to here, this is my period, this is my t, actually equal to 2 pi by omega. Actually we should strictly use omega e t e, let me say it is, I am using this way, whatever the period is. Now the roll signal may look something like that, okay, or rather let me make it dark only, no point of. Now this is roll signal phi equal to phi a cos omega t e plus e phi. I am writing it this way, okay. Now what is e phi? That is what we want to find out. First of all, we understand that here this amplitude is phi a, is also sinusoidal function, and if you see the period now, this to this, same thing as t. But what is happening is that now if you look carefully, this distance, now this I will write with respect to another color.
So wavelengths are same.
Yeah. No. See what is happening, there is a shift there. See, first of all, there is an amplitude different. Okay. So when this wave is at its crest, the roll was not at its crest. The crest of the roll, the highest roll was occurring at some other time. So the question is, the phase is very important to understand. It is a time gap between the response and the signal, the input and the output. See, this is a wave. Now at this, let me say that when the wave was at height 0, so at some time, at this is my t axis, at this time my wave height is this, but at that time my roll was so much. On the other hand, my roll become maximum at this time when wave height is so much, but when the wave height was maximum, then roll starts to drop down, so that there is a gap between response and your input and the output, wave and the roll, and this gap is given by this distance. How much is this distance? You see this distance, that is when it is 0, when it is 0, or any other equivalent point. You can take this to this same thing, because it is repeating. What is the difference, or by what this signal is in this case leading or lagging the other signal? That in this case leading, because it is occurring before, and then this, and this distance is exactly what this distance is going to be, what is we are calling this phase angle E phi. Okay, this is a measure of E phi, this part. So what is, if you actually find out from here, you will find out that the way the graph is, that this cos curve and sine curve exactly it will match this. See, one curve is just cos omega e, one is cos omega t plus E phi. Because it is plus E phi, it is occurring like this. So this tells me the phase gap between the two. Now it is very, I don't know how to explain, but in the video, but see, if you take a seesaw, if you, what you call that, there is this children's game where you do like that, and you take a spring and a ball, you do like that. Ball will also oscillate. You observe your hand and the ball motion. When you are sometime down, the ball is not exactly down, there will be a phase gap. You do, eventually you will see that sometime the ball is coming down, and at that time you start going to go up. So the ball will fall, it will go something like that, something like that, not exactly same. Okay, this is the phase gap. When you are pushing down, little later it starts getting pushed down. So then when you start pulling up, it is still going down, and then little later it goes up. So that is what is called phase gap. You see that and anything you go with a bag, go like that, you will see that the response and your hand movement, there is a difference. This is a most interesting way of looking at the phase gap. You have to understand that, because phase has a hell of a lot to do with respect to ship motions ultimately. Because if there was the same phase, you are having much more difficulty. This is a very interesting example that you should realize when you do that. Any movement, you will see that there is in a video it is difficult to demonstrate these things, but because phase is a very, very important concept, you must understand that you always write. In this case, of course, what I have done is that I have written it to be 0 wave, and this is to be, I can write, say, number of signal. I can write a signal a cos omega t plus beta 1, another one as a2 as cos omega t plus beta 2, another one, etc. All that will mean that one is happening here, another is happening here, another is happening here, and beta 1, beta 2, etc. will actually tell us the difference between the happening of the between signals. When this is maximum, the other one becomes maximum so much time later or earlier, whatever. So that is the most important part to realize as far as this phase is concerned. Now we will find out an interesting part, phase between velocity, acceleration and displacement. You see, because what happened, it is all time dependent. Now I have got roll. Now what I said is roll. When I said roll, I made actually roll displacement. Remember, that was written as phi equal to phi a cos omega e t plus e phi. Now what is roll velocity? It is going to be phi dot. If you know, that is d phi by dt. If you do that, what you get? You get here minus omega e phi a into sine e phi, and this can be written as actually here they are written omega e phi a into cos omega e t plus e phi plus pi by 2. Roll acceleration. You know, like second differentiation of displacement or first differentiation of velocity, phi dot dot equal to here omega e square phi a, cos becomes sine now. No, this will become, sorry, this is no, we are doing here, sorry. So sine becomes, this becomes cos, so it is minus omega e square phi a cos omega e t plus e phi. This can be, in order to make it so you have got this as displacement, this as velocity, this as acceleration. Okay. What do you see? Important points. Number one is amplitudes. You see that this displacement is an amplitude of phi a. What is the amplitude of velocity? It is omega e phi a. Amplitude, the maximum that can occur. What is the your amplitude of acceleration? It is omega square phi a. Okay. Now you see what happens. That is one thing you can find out, that as you go up rather, displacement to velocity to acceleration, the amplitude gets multiplied by frequency. Number one. What about phase? The phase between displacement and this thing is 90 degree. So it is actually 90 degree leading. And then this to this is another 90 degree. Or this to this and this is 90, another 90, 180 degree. So you see, when the roll is at its highest plus, then acceleration is highest minus, and things like that. When this is maximum, this is 0, this two was 0. Because when this is maximum, this will occur actually when this, the way it is, this will be 0. In other words, one will go like that, another will go maybe like that, another will go like that. And the amplitudes are all multiplied by omegas. Why I say that this is important? In fact, this graph I can just, before that I will show you perhaps, this graph is here. So I have got here phi going. This is phi. Then I will have here phi dot, and then I will have here this is what will happen. An amplitude, this will be equal to say phi a, this is going to be omega e phi a and this is going to be omega E square phi A. I mean, I don't worry about the writing if you cannot see it, but the point is to tell you that there is a relative phase gap. See, here you can see when I have got my maximum roll displacement, I have got a zero roll velocity and I have got maximum negative acceleration. Similarly, when I have got maximum acceleration, I have got zero velocity. Okay, like this. Second thing is that omega E square. See, I have got omega phi A, omega E phi A, omega E square phi A. This is very important. When you are heading into waves, omega E is going up in head. You are increasing frequency. So, the acceleration frequencies goes up even further at a higher rate, you see, acceleration amplitude, because omega E square term comes in.
Amplitude square times.
Yeah. So what happen is that also if you see, that means that if supposing, this also makes sense, something is going like this, it has some velocity. Same thing, it went much slowly, it will have much lower velocity. You see, so if a signal is repeating every 10 seconds, it has some velocity. If it is the same signal, same 10 degree was repeating every 5 seconds, it will have a higher velocity because it's going and coming back and forth in 5 seconds time. So, and its acceleration is going to be even higher. So, this is why your acceleration and velocity goes up in head waves very much. So, when you are going in head waves, you have got a very high acceleration. Why it is important? Supposing I have a equipment on a ship, some point here and equipment here. Now, this is the acceleration on that comes as a load, mass into acceleration on the, say, gun mount, for example. There is a gun there, there is a gun mount. So, naturally, if it is accelerating very much higher, then you have to account for that. So, it is not only displacement, it is not only the fact that it rolls 10 degree, but this 10 degree occurs how fast, becomes a issue. We will see later on that it is a velocity and acceleration that causes you to vomit, the seasickness. There is a certain combination in which you tend to throw up. Okay. Now we will talk about, we have to discuss this even more little bit. Now you see, in a very generic term, I will try to say about combination of motion. Now, if you see a ship here now, it is this point axis that I have found the motion, okay, velocities, etc. So, I have got here you can say a velocity vector and a rotation vector. Now, if I want, for example, to find out this point or this point how much it is accelerating at any point P on the hull, okay, you can find out the displacement, see, at xp or yp or zp as a function of v and omega. There is a relation, actually you can find out that the xp probably equal to x into g plus some omega cross, some formula is there, omega cross r or something like that. I don't recall, this may not be question, but what I want to say here is that is not important, that you can find out now, if you knew these 6 motions, primary motions, you can combine them to find out motions at any other point. Example, here suppose you take this point here P, okay. Now this will work out, this is most important point about vertical direct heave and pitch combination. We will try to work it out, this one. So combine you take a point here, some point here. Now your this height that it goes, h omega e t, this is going to be equal to z minus xb theta plus yb phi. Actually we can call it call it no, we can write it like that. See, supposing I take a point here which is located at xb yb. Suppose I take a point here somewhere which is located at xb yb. What happens is that the vertical height, how much it moves, will depend on how much this full body moves z plus how much it is pitched, because supposing this is xb, then if it is pitched by angle theta, then it will actually have a z value of xb into theta. So that is a contribution that comes out. Similarly, if it rolls, because it is not on the center line, it will have yb into phi. What I mean is that you can find out that this can be example given more. See, if supposing the ship has come down, this point will come down by an amount. So this will come down by an amount, and it has pitched further, then it will come down by further amount. So you will have here is z and here in what we call x into theta. You see, if you carefully see, essentially the displacement of any point becomes sum of combination of the heave, roll, pitch and all things. So here if I am looking at how much it is a point located at xb and yb will heave, if the ship heaves by an amount z, pitches by an amount theta, rolls by an amount phi, it will become z minus xb theta plus yb phi. Do you?
So angular movement will be there and heave will also be there.
Yes. No. So here actually this picture. Okay. Let me show this picture in a break form. Now this is my ship. So it has first just heaved. So it has heaved means it has heaved means gone up here. So it has heaved here. So the ship has gone up by this much. So this point has now gone up. Earlier it was here, so it has gone up by an amount z. Okay, see, supposing this ship was here and the point was here. This is my point P. So this point, now the ship has gone up by amount z. Therefore, this P point has gone up by an amount z. Okay, point 1. Now on that, now this P point is now, I just draw this line P point. This now my P point is here. This is my axis. This P point has gone up by z. Now this P point is going to have a pitch. Now pitch positive is down, so it has got pitch of theta degree. So it now it has pitched by theta degree. So now it has come down by an amount of xb into theta. So now this height has become plus z minus xb theta. Okay, so this has become this distance is plus z minus xb theta. Now if you see this point to be actually on the roll side, actually here the ship has rolled further. So as a roll, this point would have come down by this much distance, which will be yb into phi. So if you add them all up, this point's total vertical displacement, the total vertical displacement is going to be the rigid body displacement because of the ship hull, that is the ship's heave, plus depending on its location and the pitch of the ship. So the pitch of the ship would make it to go up little more or down, and roll of the ship also is going to make it go up or down. So therefore, you can, if I knew this z and theta and phi, for any point I can combine them to find out what is my desired displacement. See, there is a crane point here. You want to find out how much this crane point will go up. Okay, so obviously it will go up. First of all, if the ship has heaved 2 meter, it will go up 2 meter. But it has also pitched. Because of pitching, it has gone up by some other angle. Also rolled by some other. So you can add them up to get the total. That is the point I am making here. Okay, so it can be linearly combined to find out these motions. Very simply. Now why I say that? Because you see, this interesting part is that if you linearly combine here, so we start with this here again, z minus xb theta plus yb phi. Now I am writing all this in combined form. See, z was my za into cos omega e t plus eta z. This was my z minus xb was xb, theta was theta a into cos omega e t plus epsilon theta, and y was plus yb into phi a into cos of y e t plus e phi. If you do this algebraic manipulation without this thing by algebraic I just write here by algebra, you can, this will turn out to be equal to minus of plus ZA sine of Ez minus xp theta a of sine of E theta plus yb into phi a into sine of E phi into sine omega t. Okay. See, what happens is that you can write, if you do algebraic manipulation, add them all up, cos a plus cos b as cos a cos b, etc., etc., it will turn out to be an expression of something into sine omega et, okay, which you can write as equal to, as if HA into cos omega et plus EH. See, you can express this full thing again as a sinusoidal function. Now, my point of saying all this is that this, when you combine them, this is a sine curve, this is a sine curve, this is a sine curve. You add them all up, that what you get, this expression will also be a sine curve with an amplitude and with a phase angle. This becomes equivalent to that. You can actually work out how much is HA actually. It will turn out that HA will here become H. One can find out this various ways.
This ultimate value will be at a particular instant.
No, that's no. See, okay. Let me.
It's always changing.
Yeah, let me just complete that here. Then again, I will write now. Therefore, what we get H omega E
So
t.
here H we are denoting the
Vertical distance. See, it is becomes HA into cos omega E t plus EH, where HA cos EH is equal to plus ZA cos EZ minus XP theta A cos E theta plus YB phi A E phi, etc., etc., and HA becomes you can find this HA and E alpha expressions as function of, let me write you ZA theta A phi A EZ E phi E theta. Basically what happens, you will get an algebraic expression. Never mind the algebra, it's a tedious algebra, all right, but you get an algebraic expression which will tell me that this can be expressed as this form. Now you are asking this question whether it is instant time. No, this is actually height at any time omega e and any time t. So you see, the point has a vertical displacement. Obviously that is changing with time. Any time it has value. That will obviously can be expressed as something into cos omega t plus e alpha, which means that can also be expressed as if it has an amplitude and a phase angle. This is not, this HA is not changing with time. Obviously H is having a time function because H is a function of t. Why we say that? The reason we are trying to say is that if you combine motions which are sinusoidal, it turns out that motion at any other point also is a sinusoidal, and the amplitude of that motion at any point and the phase can be simply by written in terms of the amplitude of those, the location of the point. Of course, the location of the point will come here, x b y b. So it becomes function of, I can write, of ship motion plus point location. If you know the point location, if you know the ship motion parameters, that is heave, roll, pitch, the primary motion, you can combine them and motion at any point becomes nothing but some kind of combination of those. That's all. But it is also a sine function. The most important point is to say that it is also a sinusoidal function. So you see, now if this is sinusoidal function, you can now find out h omega this is also sine function because it becomes nothing but omega e into HA minus into sine, etc. And h dot dot also becomes a sine function. So I'll just sum it up. See, it basically I'm trying to say is that h becomes h omega also becomes a sinusoidal function, and so is h omega dot dot. So if you plot now, you will find that supposing I start with the this may be my wave, and it will, if you do work it out, it may be that this might be my h. So what I am trying to say, and obviously then this will become my so-called h. See, it is the interesting point of this is that to get motions at any other point or anything that you want, everything is dependent only on those first 6 motions. If I have figured out by heave, roll, pitch, yaw, start, sway, heave, roll, pitch, yaw, then anything else that I want to know, any damn thing else or anything in any point, anywhere, whatever, it will turn out that they are all expressible in terms of those basic parameters, and they are also a sinusoidal function. And any sine function, the unknown thing is only 2, one is the amplitude, one is phase. So therefore, suppose I want to find out for a ship, let me give an example. I want to find out, you want to know what is my acceleration. There is a deck crane here, you want to know what is my acceleration at this point. If I want to know that point acceleration, I actually know it is sinusoidal function. I will know everything, every time, every instant, what is the value of that acceleration, provided I knew start, sway, roll, those 6 motions and the location of the point. Of course, the location is a geometric parameter, so I would know. Why we say that is because it turns out that ship motion therefore is primarily dependent on those 6 primary motions. So our biggest challenge would be to find out those motions. Once you find it out, those motions, the complication is maximum to find out those motions. So I just write the summary. Find that is, surge, etc. yaw. What do you find? Find amplitude plus phase. So if you can find this, you can combine these all together, get what you want. I'll write that way. You see,
By phase you mean the wave angle?
yeah, no, not wave angle. The difference between when it is occurring with respect to the wave. Let me say when it is occurring with respect to the wave. If you know that, the rest part is pure simple algebra. So what, I'll stop here because I want to now, obviously knowing that, we have to figure out how we can find the basic motions. That is the most biggest challenge, which we don't see. As a practitioner, most practitioner will be bothered about this because what you want is what is ultimately you are interested. But to get from here to there is actually algebra, simple algebra. To get to this point is the most difficult point. But here to here is absolutely simple algebra. It is just question of 2 more pages of just doing 1 plus. It is like if you have to add 10 tables in a figure, it is just tedious but nothing brainy.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning, with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology, and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems, and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body. Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.